This really is a critical part of the year. It's such an important time to build a really strong foundation. Once you get this, once it makes sense to you, I think the rest of the course will flow, just like this stream. I think it'll make a whole lot of sense to you. But if you don't get this, then I think that a lot of what we're trying to teach you, you will find frustrating. Okay, so without any further ado, let's work some more with linear equations, and we're going to throw in a touch of fractions, decimals, and percents today. And don't forget, we got a quiz at the end of the period. All right, so solving linear equations, solve and check. Let's do the stop and start technique. You can get going on this right now, and I will give you the answer in a minute. This is just like the one we ended class with the other day. Okay, so now that you have your answer done, here is the work that we put. Now, the first thing I notice when I'm looking at this is a same side situation. If you notice, we have the x's on the same side, and on the other side of the equal sign, we have numbers on the same side. Since the x's are on the same side, I do same side, same operation. I combine the like terms. 3x and negative 4x makes negative x. On the other side, 1 and 12 make 13. Now I have an opposite side, opposite operation situation. Always start with the smaller number of x's. Negative 2x's is smaller, so I add 2x's to both sides. Negative x plus 2x, that would be 5 plus 1x. 1x is what's left, equals 13. Subtracting 5 from both sides, I get that x is equal to 8. Now, if you notice on these directions, it says solve and check. So there's my check. All I do is substitute the correct answer, 8, into each of the places I find an x in the original equation. This is extremely important that you put it in the original equation. If you check it in this second equation, this is called a derived equation. And if you check in a derived equation and you make a mistake from the original to the derived, you'll never know that it was a mistake in the original equation. So very important to check the 8 in the original equation. You can see there that it checks because both sides equal negative 3. So that scale we spoke of, the balanced scale in science class, stays balanced. Okay, another one for you to try, a little stop and start. Okay, so the first thing I do is I distribute the negative 2. All right, extremely important to notice that. So I do negative 2 times 3x. The negative 2 is outside the package of the parentheses. That's negative 6x. And then negative 2 times negative 1 is plus 2. Then there's a plus x equals 14 minus x. I didn't touch that. Looking at it like Peyton Manning coming to the line, I'm saying, okay, is it same side or opposite side? Well, I always look same side first. And there is a same side going on here with the x's on the left. And that gives me a negative 6x. And 1x is negative 5x. And now I go into my opposite side, opposite operation, audible, just like Peyton Manning would do. I add 5x to both sides, again, starting with the smallest number of x's. That leaves me with 2 is equal to 14 plus 4x. Now the numbers are on opposite sides, so I do the opposite operation with the numbers. That 14 is a positive 14. Don't ever forget, we always look in front of the number to see if it's positive or negative. Just like we look in front of the name Lindquist, Mr. or Mrs. Lindquist, to see boy or girl, we look in front of the 14 for the same thing. There was a positive 14, so I do negative 14 or subtract 14 from both sides. The reason I do that has absolutely nothing to do with this plus in front of the 4x or this positive. I don't look at anything as plus or add. I look at it all as positive or negative. The 14 is positive, so I have to do the opposite, which is negative. That leads me on the left with negative 12 equals 4x, because 14 and negative 14, Sasquatch squishes, alien abduction, die. Little old lady cancels it out, whatever you want to say. Dividing both sides by 4, and I get that negative 3 is equal to x. Don't forget, if you were going to check, you must check in the original equation, not the derived equation. All right. So this is a little bit of a new example for us to do. There's a relationship between the number of words in a child's vocabulary, V, and the child's age, A, in months, for ages between 15 and 50 months inclusive. Now, If I were a kid or a young adult student reading this, I would be going, what the heck? Oh, come on. Then the next line says, this relationship can be modeled by the formula. And I'm like, oh, well, wait a minute now. They're giving me the formula. So, in other words, all that stuff in the beginning paragraph, that all comes up to mean mathematically, if I take the vocabulary and add 900, I get 60A, A being the age in months. So here's an example of how we can use formulas like this to arrive at conclusions. Use the formula to find the number of words in a child's vocabulary at the age of 50 months. So all I have to do is substitute in a 50 for A, because the age is 50 months. Okay, I substitute 50 for A. 60 times 50 is 3,000. The V plus 900 was already part of the formula. You didn't even do anything to that. And then I just subtract or do the opposite, minus 900 from both sides. Look at it as negative 900. It doesn't matter. On the left, we're left with V. And on the right, 3,000 and negative 900, or 3,000 take away 900, however you want to look at it, is 2,100. So, therefore, at 50 months, a child will have a vocabulary of 2,100 words according to the formula. Right? So, what I wanted to do on that one was just show you a little bit of how we can turn words into equations now. We're stepping past expressions, and then we can just solve the resulting equations. And over the next couple of lessons, we're going to get more and more into word problems. Now, here's the fancy sort of stuff. The addition of the properties of equality. This is the kind of thing that you read in a jargon book for math, for people who are, well, math geeks or mathematically inclined, if you would say. Addition property of equality. The same real number or algebraic expression may be added to both sides without changing. We did this when we said that an equation's like a scale. As long as you add the same thing to both sides, scale stays balanced. Picture of equality. And the same thing is true of multiplication. All right, as long as it's not a zero, you can multiply both sides of an equation without changing the equation solution set. So the whole key here is do the same thing to both sides, and it's going to work. That's really what we've been getting at over the last couple of days. Here's a couple of examples. On the left, notice what they do is divide both sides by 5. On the right, two ways to look at it on the right. You could say that they are dividing both sides by 2/3. But to divide by 2/3 is the same thing as multiplying by 3/2. So it really is the same exact thing. When they write the 3/2 over here, dividing by 2/3 is multiplying by 3/2. Remember elementary school, when you would flip if you were dividing fractions, you flip the second one and multiply? That's what it's getting at there. So you've been using it all along. That's the main point. I wouldn't worry too much about the equations. You have been doing this technique all along. Okay, let's do a little stop and start for this equation. All right, so first step, add 4x to both sides. When I do that, I should actually take a step back. That's the second step. The first step should have been, is this a same side situation or is this an opposite side situation? I kind of rushed through that. Clearly, this is an opposite side situation because here's your equal sign, and the x's, the negative 4x and the 2x, they can be found on opposite sides of the equal sign. So starting with the smaller one, it says negative 4x, I do positive 4x. 2x's and 4x's over here make 6x's. Minus 15 is 21. Adding 15 to both sides because now the numbers are on both sides. Again, this looks like your standard two-stepper. This is, you're just cleaning up the situation. This is very comfortable. We're very used to this. We wish all the questions on the test were like this. 6x is 36. And since we're multiplying by 6, we do the opposite and divide. X is equal to 6. Okay? All right. So let's do a little bit more here with these word problems and so on and so forth. I'm going to give you a little bit to read through number 4 and then do number 4A. I will put up, excuse the yawn, I will put up the answer to 4A and then we'll do a little stop and start also for 4B. So stop and start moment, read through, answer 4A. Then we'll stop and start again for 4B. Okay, so what you have here is you have a bar graph. That's what's in the box. And it says in 1940, a Westie would cost $765, and in 2009, it would cost $2,000. Using today's dollars, the data can be described by the math model, the equation, P equals 18N plus 765, where P is the puppy's price and N is, very important here, the years after 1940. So whenever we get a formula like this, P equals 18N plus 765, we just want to take a step back and make sure we understand what each of these variables are. In this case, P is the puppy's price. It's a great variable to choose, better than X, right? And N is the number of years after 1940, not overall, after 1940. So, does the formula underestimate or overestimate the price of a puppy in 2009? Well, the first thing you have to understand here is that N is 69. The reason that N is 69 is because in this bar graph, we're dealing with the year 2009 and 1940. So N stands for the number of years since 1940. So I subtract 2009 minus 1940. Then I start working this into the formula. The puppy price in the formula, in the bar graph, is $2,000. Let's plug in the 69 in for N, because 69 is the number of years. Let's see how accurate this formula is. 18 times 69 plus 765. Now, this is just evaluating a formula. We're not like, adding and subtracting something to both sides or multiplying or dividing, because everything's on one side. 18 times 69, plus 765 is 2,000. So the bar graph underestimates by $7. The bar graph says 2,000. It's really 2007. Okay. So I always look at those as easier than solving equations per se, because you're just substituting the value in. But they can be tricky. The thing that makes them tricky is the reading, not the math. The math's pretty easy. If I told you that every question on your final exam would be like 18 times 69 plus 765, you would say, oh, sign me up, man. I am so all over this. But the truth of the matter is that you had to know what to do by reading the problem in order to be able to do that. And last, if the trend given by this formula continues, what will be the price of the puppy in 2151? Little stop and start here. It's important, little hint, hint, hint. 2151 is P this time, and you got to solve for N. Okay, so 2151 equals 18N plus 765. Sorry, I forgot to make this one in red. It's in black. I subtract 765 from both sides. I'm trying to squeeze it in here. And I get 1386. Then I divide by 18. Pretty straightforward. N is 77. And then I have to add the number of years to 1940, because that's what N stands for. 1940 plus 77 is 2017. So in 2017, the price will be 2151. All right, time to record this.